we're going to assume two impulsive delta V's. So there's sort of two assumptions there. One is that they're impulsive delta V's, and the other is that there's only two allowed. This means that the velocity change maneuvers are instantaneous, and you only get two of them. Instantaneous means that they happen without the passage of time. You had a certain velocity, and then instantaneously you have a new velocity. That's the assumption of an impulsive maneuver. And then the third assumption is that the orbits of the rocket and the station are circular and coplanar. The first two assumptions, Newtonian gravity and impulses, imply that the orbits will be Keplerian, that is, the orbit of the spacecraft in doing its transfer. It'll always be on a conic arc. After an impulse of delta V is done, we simply have a new value of velocity, and then we continue on in free fall, ballistically, to trace out a Keplerian or trajectory or conic trajectory. That means that because we have Newtonian gravity, the total mechanical energy is conserved, and secondly, the total angular momentum is conserved. And so these two conserved quantities allow us to solve mathematically for the delta V's involved. Now, are these assumptions always correct? No. It depends on how accurate and how simple we want our calculations to be. So, for example, we know that the Earth is not actually a point mass. It's got mountains on it. So it has high points, it has low points, and so it is not a perfect point mass. And you know that there are more complicated gravity models for the Earth. We also know that a velocity change actually does take time. However, when the rocket only takes, say, a minute to do a delta V or a few seconds, that might be considered a small enough time to consider it to be no time at all, and therefore instantaneous. But in reality, it does take time. So there's an error assumed, built into your assumptions. And the orbits could be inclined to each other, okay? And then that means you have to worry about inclination changes, which is not dealt with in the Hohmann transfer. And another question is, what if the two impulsive delta V's is not the limit? What if you are allowed more? What if you allowed three impulsive delta V's? What if you were allowed a series of impulsive delta V's that would eventually look like continuous thrust, like you get in electric propulsion? Then can you use the Hohmann transfer? No. So, and another thing is, what about the gravity of the moon or the sun? Other forces such as drag. So you see that the Hohmann transfer has these built-in assumptions, and yet it is probably one of the most often used orbital maneuvers in the space program. So in spite of all of those limitations, it's very, very applicable in many, many cases. So now we're going to derive the delta V equations for the Hohmann transfer. And so we'll assume that we're starting off in this initial circular orbit of radius r1. Okay, so here's our planet, could be any planet. And we're in this small circular orbit of radius r1. And we have a velocity v1. And this velocity is what is known as the circular speed. Right here, we can compute it by the square root of mu over r1. And I'll be using this picture quite a bit. We're going to perform an instantaneous delta V parallel to V1, and then the spacecraft will coast on this elliptic trajectory to R2. So this is the radius R2. And at this point, the velocity will drop to v2. It's a lower value because you throw something up, it slows down as it goes up. And then if you did nothing, it would continue on back down where it came from, like this. And it would repeat and be in this elliptic orbit from then on. However, you do something when you get up here. you do this delta V2, and it's a circularizing maneuver such that the total of these two values is the circular speed to stay in this orbit up here at R2. So we start from a circular orbit of known radius, and we can compute the circular speed immediately. We want to end up on this final circular orbit, which has a speed of the square root of mu over R2. So these are both known values. And what we're going to try to do is we're going to solve for this elliptic orbit, which is called the Hohmann transfer orbit. It's